What's up everybody? How you doing? How you doing? Welcome to my latest video, how do we simplify roots that contain variables. We've already covered how do we simplify square roots, we've covered how do we simplify cube roots, and now we're going to talk about what happens when the radicand is not a constant, it's not a number, but it's actually a variable. So let's jump right into it. Steps are kind of similar. What you need to do is find the largest perfect square or perfect cube that divides the radicand evenly. You'll know if you're looking for perfect squares or perfect cubes by looking for like the little index. If the index is a 2, you're looking for a perfect square. If the index is a 3, you're looking for a perfect cube. If it's a 4, you're looking for a perfect fourth, we'll call it, and so on. So always pay attention to the index here. The perfect variable squares and cubes are very easy. If you think about perfect squares for variables, it's just x squared, x to the 4th, x to the 6th, x to the 8th, x to the 10th, and so on. We're talking about any exponent that's a multiple of 2 because the index is a 2. If you're looking for perfect cubes, we're talking about x cubed, x to the 6th, x to the 9th, x to the 12th, x to the 15th, and so on. Those ones have exponents that are multiples of 3. If I was looking at something that had an index of, let's say, not 3, but an index of 4, you could imagine the exponents would go x to the 4th, x to the 8th, x to the 12th, and just multiples of 4. What you want to do afterwards is rewrite the radicand as a product. The product is going to contain that perfect square or perfect cube from before. And remember, when you're writing a product for variables, you would add the exponents. You're not going to be multiplying them because if you have variables with the same base and you multiply them, the rule is to add the exponents. And finally, let's simplify. Some of these are actually end up being perfect squares or perfect cubes, so there's not much to do. Let's jump right into a problem. I want to simplify the following roots here, and the first step would say find the largest perfect variable square. And if I look on this list here, I can see x to the 16th is a perfect square. So this one is just going to simplify very nicely. So I could actually rewrite this one in rational exponent form or just with an exponent, remembering that this piece here is the numerator and this piece here is the denominator. So for the perfect square, maybe I write it like this. This form here is radical form. This form here is just exponent form. Maybe I'll put an R there for radical, E here for exponent. And here I could just divide 16 divided by 2, and this here is just x to the 8th. Because this was a perfect square, it worked out perfectly. And if you think about it, remember the whole meaning of square root. It says what number times itself twice is x to the 16th, or in this case, what variable times itself twice is x to the 16th? Well, x to the 8th times x to the 8th would have been x to the 16th when you added the exponents. Let's look at the second one. The second one is not a perfect square. X to the 13th is an odd power, and only the multiples of 2 are perfect squares. So I take out the largest perfect square that divides it evenly. In this case, x to the 13th would be here. So the largest one that divides it early is x to the 12th. So what I can do is like make a list of like perfect squares and non-perfect squares. The perfect square here is x to the 12th. Well, x to the 12th times what variable is x to the 13th? Well, because we're adding the powers, it's just x to the 1st. Now I simplify. Just as you saw this one here, I took 16 and divided it by the index of 2. I can take 12 and divide it by the index of 2. That's just going to be x to the 6th, and this piece will remain unchanged. And then, of course, it's very commonplace not to write the 1 here and not to write the 2, and I could just simplify it like this as a final answer. Let's look at number 3. Number 3, now we're looking at perfect cubes, so we're looking at multiples of 3 for the exponents. When I want to find the largest perfect cube that goes into x to the 11th, x to the 11th is right here, so the perfect cube must be x to the 9th. That's like the largest multiple of 3 I reach before I hit 11. So if I'm making my list of now perfect cubes, I would put the cube root of x to the 9th, and I think x to the 9th times what variable expression is x to the 11th? Well, that's going to be x squared, considering that I add these powers. 9 and 2 would be 11. I can simplify this one by taking the exponent of 9 and dividing it by the index of 3. 9 divided by 3 is x to the third, and the non-perfect cube piece remains unchanged. This one simplified nicely because of the 2 and the 1. This one, there's nothing to do here. Let's see if you can try one of these on your own. See if you can find the equivalent expression here. If we go to rewrite this one, we could put in the index of 2 if we want. These two pieces are equivalent. When the index is not written here, we know it stands for a 2. And x to the 36, because it is a multiple of the index of 2, it is a perfect square. So what I can do there is I can just rewrite this in exponent form if I want. That might be a step that I can do in my head and skip. And 36 divided by 2 is x to the 18th. Let's see if you can try another one. In this case here, x to the 9th for a square root, that's not a multiple of the index of 2, so this is not a perfect square. So I want to find the largest perfect square that goes into x to the 9th. If I count my multiples of 2, 2, 4, 6, 8, x to the 8th would be my largest perfect square. X to the 8th times what variable expression is x to the 9th? Well, that's going to be x to the 8th just times x as we're adding the powers. Here I can simplify 8 divided by 2 is x to the 4th. And if you noticed, even when I was counting multiples of 2, I went 2, 4, 6, 8, and that kind of gave us a hint for x to the 4th. And of course, I don't need this little 2 here. I don't need to write to the power of 1. I could simplify that just like this. Let's see if you can try another. Here when I rewrite this, and I'm looking at my perfect cubes now, and if you look at the multiples of 3, 3, 6, 9, x to the 9th is a perfect cube. If you want, you can put it in rational exponent form. Rational just really meaning fractional exponent. 9 divided by 3 is x to the 3rd. Let's try another. Here, x to the 13th is not a multiple of 3. 3, 6, 9, 12, and then 15. So the largest power that I reached before I got to 13 was x to the 12th. I will put that on my perfect cube list. X to the 12th times what is x to the 13th? Well, 12 plus 1 is 13, so it's just the third root of x to the 1st. Now I can simplify. 12 divided by 3 is x to the 4th. And I get this, which we know I don't need this 1 here. I could probably simplify this just like that. Let's try another one. Here, x to the 38th is not a multiple of the index of 3, so this is not a perfect cube. So I need to find the largest perfect cube that we're going to reach before we get to 38. If you did that correctly and you rewrite this as some perfect cubes and non-perfect cubes, you should get x to the 36th. X to the 36th times what is x to the 38th? Well, 36, you'd have to add 2 to get to 38, so it's x squared. Simplify the perfect cube. 36 divided by the index of 3, that's just going to be 12, and I get the x to the 12th times the cube root of x squared. Let's try another. See if you can simplify this one. This is the first one we've had with a perfect fourth, we'll say, and this one here, because 16 is a multiple of 4, 4, 8, 12, 16, it's just a perfect fourth, so I can put it in fractional form or rational exponent form if I really want. 16 divided by 4 is x to the 4th. Let's try another. Here's another one with an index of 4, and here we're dealing with x to the 13th. 4, 8, 12, 16. So this is not a perfect fourth. So I need to find the largest perfect fourth that goes in. 4, 8, 12. It looks like it's x to the 12th. And x to the 12th times what will be x to the 13th? Well, because I'm adding the exponents, 12 plus 1 is 13. So I'll write this as x to the 1st, not 3rd. And then I just want to simplify that there. Here I am going to divide 12 by the index of 4. I will get x to the 3rd And here I'm going to get, it looks like just x there, or x to the first, which isn't an answer choice. So if you solved this one and you didn't see a possible answer choice, that's a mistake on my part. My bad. Let's go on to the last and final problem. Hopefully there's a correct answer for this one. Here I want to see if you can find the 7th root of x to the 37th. Well, if I go and I rewrite this, I'm looking at multiples of 7. And here, this one might be pretty bad, as this one here says 23. So let's try it with 37. 7, 14, 21, 28, 35. 35 looks like the biggest one. It's going to reduce to x to the 5th. So if I write my perfect 7th, I get x to the 35th. X to the 35th times what is x to the 37th? Well, 35, 36, 37. It's x squared. We know the non-perfect 7th won't reduce, but this one will. 35 divided by 7 is just x to the 5th for a final answer. I hope you've enjoyed this video. I've enjoyed showing you how to simplify variable roots